Back to Laplace transforms and its inverse. Today we are going to tighten up some loose ends, prove that inverse Laplace is linear. You had trouble with it on the homework. And also I want to share with you a couple of tricks and maybe do one simple example. Next time we'll introduce new concepts. For today, I'm just going to keep it short and just tighten up some loose ends. So the first thing we need to do is prove that Laplace is linear. And the first thing you need to realize is, what does that mean? You need to be able to write it properly. All it means, if you apply Laplace inverse on this combination, you don't see little f and little g. Those are applied through L, right? You apply Laplace on little f to get the capital F, and therefore you apply the inverse on capital F to get little f, okay? So the first thing to realize is to be able to write this properly. This is what we want to prove. Now, I noticed some of you use integrals and all that stuff. Why would you want to do that when you already used integrals to prove the linearity of Laplace transform? This is the very first property we proved in this unit. So you don't want to reinvent the wheel. You want to use what you know to get what you don't know, okay? So I don't want to see integrals. It's just a waste of time. You could do it. I mean, it's no problem, but you're just making it a little harder on yourself. So I'm going to use the fact, this property. That's all I'm going to use, okay? Now, Laplace transform of a little f as a function of time is capital F, and therefore inverse Laplace of capital F is little f. The same thing goes for g, okay? I'm going to use this fact, and I'm going to play with these because I need capital letters. So I need to use these to get to here, okay? So I'll begin with the left-hand side of my property, which has been proven, this one. Laplace of AF plus BG is exactly Laplace of A inverse Laplace of f of s. I replaced f of t by this. That's all I did. And I replaced g of t by that. Would you agree? So this is the left-hand side of my property. And I can use this anytime I want, okay? Now, the right-hand side is A capital F of s plus B capital G of s. So this is exactly this, okay? So I haven't done much at all, and you're almost done with the proof. So now, think about it this way. Laplace of some function is this. Therefore, inverse Laplace of this has to be this stuff inside. So I copied the stuff inside, which has to be inverse Laplace of this quantity. And we're done. Because this is exactly this, and this is exactly that. Therefore, Laplace inverse is linear. And therefore, we can use it anytime we want. Because we always have to find Laplace on when you solve ODEs, you apply Laplace on both sides of an ODE. You take advantage of the properties of Laplace, and you get it in terms of s, and then you want to use inverse Laplace of functions. They usually look like rational functions of s to get the solution called y, okay? And therefore, we have to use this property over and over and over again, okay? So that's the first thing. And here is a great example. Isn't this the third step in how you solve ODEs? So I give you an ODEs, you apply Laplace on both sides, then you turn it into some equation, then you clean it up nicely, and then you apply inverse Laplace to solve for y. So we need to be able to take advantage of properties about inverse Laplace. I am not going to do this, okay? I know you know how to do this, but you made a lot of careless errors. So I'm just going to show you some really nice trick, okay? So what you did was you wrote A, B, and C, and you wrote three terms, and you said A times these two plus B times these two plus C times these two quantities have to be the top. and the bottom is the bottom. You don't have to write it. And you lined up your squares and your s's and your constants, and you lined them up, and you solve for a and b and c, and you should have gotten a equals 1, b equals -1, and c equals 2, I believe. Many of you got fractions, and that's okay because, we make careless errors. And I know you know better. The problem is you didn't test it to see if it works. So when you get like a third and a 5/8 and -2/3, well, you got to cross multiply to see if you get this. For otherwise, your ODE will be incorrect. So that's not what I'm going to do. I know you know how to do this, okay? I'm going to show you a shortcut, and here's the shortcut. So you write this in this format, okay? And in order to find A, what makes the bottom 0 is 0. So what you do here is you replace S by 0, and you ignore this, you hide this factor completely. Because if you don't, you're going to get 0 at the bottom anyway, and that's a problem. So to get A, you replace S by 0 but by hiding this factor. To find A, replace S by 0 on the left-hand side and hide S. So what do I get? I get -2 over 0 plus 1 times 0 minus 2. Here you go. Done. A equals 1. So fast. When I was writing this down, I thought I was finding B, but I was actually finding C. So I'm going to do C next. To find C, go back here and you replace S by 2 and hide this factor. Okay? So you get 2 times 2 squared plus 3 times 2 minus 2 over 2. 2 plus 1, ignore. That's all I did here. And I got C equals 2. All right? And to get B, which is the last piece, you go back here and you replace S by -1 here. -1 squared times 2 plus 3 times -1 minus 2 over -1, -1 minus 2, and ignore S plus 1. That's all I did here. And I got my B, and life is good. So, so this is really cool. So the inverse Laplace of this has to be inverse Laplace of that. And because we just proved that inverse is linear, feel free now to distribute L inverse, so to speak. We're not distributing. It's not. We shouldn't say distribute. These are not numbers, okay? The constants can come out. The 2 can come out. I got that. And inverse Laplace of 1 over S is 1. Inverse Laplace of 1 over S minus A is e to the AT, but A here is -1, so I got that, and that minus went here, and that 2 went here, and in here A is 2, so you just do e to the 2t. You're done, okay? By the way, I'll be curious to see if you could find the ODE whose solution is this. So generally we give you an ODE and we ask you to solve for y, or y of t. Well, this is the ODE, and it is particular. There are no constants, like C1 and C2. Is it possible to find the ODE? I could see that probably this is coming from the homogeneous piece. And if you use the characteristic equations, you'll know what to do on the left-hand side. Now, the forcing function might be maybe just 1. So therefore, now the solution, the particular solution is 1. So what is the forcing function? Okay. I don't know if I'm going too fast here. So if I have a2 of ty double prime plus a1 of ty prime plus a0 of t y equals r of t. Let's kill this one, because remember we always divide by the coefficients of y double prime. Is it possible, my question to you is it possible to look at the solution and see if you can produce the original ODE? I'm just curious. I haven't done it, but I'm sure you could probably pull the function. So that's one thing. Just by looking at this, it looks like this is coming from the homogeneous and this is coming from R of t. This is not R of t, but that is the solution. This is the particular solution that came from R of t. So I'll be curious to see if you could pull it, okay? Because it doesn't look hard at all. Okay, so that's that. So I hope you appreciate this trick on how to find A, B, and C. The next thing I want to do is there was one question that I asked you to do, and I'm not going to go over it. It's easy, but I want to show you a trick. The question I ask you to do is prove that Laplace transform of this product is this. Now, you could probably see it coming because think of Laplace of polynomials. Laplace of polynomials is this, right? And you may remember that Laplace of e to the at is just 1 over s minus a. In fact, we proved in class that Laplace of e to the at times any f is the same thing as Laplace of f, except that we replace s by s minus a. So there is an s here, you may remember, right? So anytime you introduce e to the at in front of some function, you're going to get Laplace of the function itself, but then there is a, let's call it a horizontal shift, so to speak, right? You don't get 1 over s, but you get 1 over s minus a, okay? So when I look at this, I look at this as my function, f. So Laplace transform of this should be Laplace transform of just t to the n, which is that. However, because we're hitting it with this function, we're going to take this one and we're going to shift it to the right by a. So I should expect, this is not kind of a proof, but I should expect n factorial over s minus a to the power of n plus 1. I should expect that, okay? This should make perfect sense to you, okay? So now, the reason I went over this because I noticed you don't have to, even though now you know a shortcut here, sometimes if the bottom looks like s to the fourth, you know, like let's say you're given something like this. Find inverse Laplace of 1 over s to the fourth. Well, you don't want to write s to the fourth as a over s plus b over s squared plus c over s cubed plus d over s to the fourth, trying to use partial fractions correctly. Even if you use the shortcuts I showed you, why bother? Because we like s. We like s plus 3. We like s minus 20, and so on and so forth. Why? Because we have this. We have this, my friends. We have this. We have that. This is like s to the fourth when n is 3. So I just threw at you this example, and I really don't want you to use partial fractions at all. So I notice that this looks like that and like that. In other words, looks like this. There is a shift to the right by 1, so a equals 1. And the power here is 3. That means n must be 2. Therefore, based on this, 2 factorial over s minus 1 to the third is exactly what I have. Of course, this is 2 over s minus 1 cubed, but I don't have 2, I have 6. That's no big deal. That's no big deal. Inverse Laplace is linear. I can pull a 3 out. So inverse Laplace of 6 over s minus 1 quantity cubed is 3 times inverse Laplace of 2 over s minus 1 cubed. Now you already know the inverse Laplace of 2 over s minus 1 cubed, right? It's going to have to be e to the 1t t squared. I'll repeat it in a different way. This means that e to the at, t to the n, is inverse Laplace of n factorial over s minus a to the power of n plus 1. Okay? So I have this. So I can write it like this. So you get e to the 1t to the power of t squared, because n is 2, and the 3 just dragged itself, and I already know my solution. So there is no need. So if somebody asks you to find the inverse Laplace of 6 over s minus 1 cubed, I really don't want you to do this. You know this from calculus. If you have a perfect cube or a perfect square, you have to repeat your factor many times, right? Even with the shortcuts to find a and b and c, you're kind of wasting your time, okay? You really want to take advantage of properties like this one. So you can go back now. You can go back to the list of the table we proved, you know, that table on the right hand side, and add this one to it. Okay, this is a combination of this one and that one. Okay, and think of this as just does nothing to f except shifted it to the right by a, so to speak. Okay, so that's another trick. This video is short. Next time we're going to begin a new unit. I have 3 ideas and I don't know which one I'm going to do first, but this should do it for now.